investigations very much led to inspiring and informing things that happened in robotics. So just a handful of years later, there was this 1970 copy demo at MIT, some very cool demos that you can see online if you look at the website. And this sort of blocks world setup very much inspired that. And then in turn, the limitations and the challenges that we're seeing in these sort of robot demos then came back and fueled, okay, what types of research problems should we be working on? So one of the main challenges, according to the formulations in the robotics at the time, one of the main challenges was, hey, we're trying to detect all these blocks, and the way that that worked was by doing edge detection. And that was, again, I'm leaning on Steve Seitz' summarization of oral histories here, was one of the main reasons that there was so much research in edge detection over the year, leading to things like canny edge detection. Whether or not that was the best idea is sort of, we can view that maybe a little bit differently from hindsight now, that maybe not everything is about detecting edges, but of course it's a very useful sort of building block in computer vision. So this is a very brief sort of one-slider, but again, just wanted to call out that there's been a very intertwined history of the two fields, and we're excited to talk more today about where they're at now. Cool. So I guess I can introduce Andy Zhang, who I work with a lot at Google, and I love working with Andy. And Andy has put together this awesome collab based on some things that we've been working on. And honestly, I think it's like just such a great, I honestly think that you could get an entire PhD out of basically, adding a few variations of 100 different lines of code in this way or that way to this collab. It sort of has everything. I think it's really nice. And Andy's going to walk you through it.
Okay, cool. Let's give you the link to download the collab. So if you go to the URL, not sure if you can still see the screen. Okay. If you go to socraticmodels.github.io and go to code, you'll find it on the bottom link here, open in Colab. Also, throughout the duration of this tutorial, it's meant to be interactive. So if anybody has questions, you're running things on your laptop and something breaks, please feel free to wave your hands and ask us to slow down or whatnot.
You need to share the tab.
Oh, okay. Michael, can you see the screen? Still black. Okay. You can see that. Okay. All right. Yeah, so. Okay, cool. Yeah, so once you've got the links, then this is what it looks like. This is a copy that's running on my instance, but yeah, some of the headers here are just giving an intro to Socratic models, but I think we'll get to that a little bit downstream. So the first thing to note here is that there's a setup section. It's going to install a bunch of things. Notably in this collab, there's going to be a simulator, so that's PyBullet, and that'll be running in server side. Oh, and actually, before jumping into a list of packages, for those that just want to get something running already, there's 3 steps for the quick start. First, registering for an OpenAI key, a GPT-3 access. When you register for an account, there is a couple dollars that are free, so that's enough to run the demos that are in here. And really, it's only needed for the very last step, but some of the sort of human to robot type interactions are fairly interesting and only possible because of this. And so definitely recommend. It's not strictly necessary, but I think it's definitely recommend trying it out. Changing run type to GPU and then run all. So the GPUs, this collab also has training code baked into it. So if you scroll all the way down, you'll start to see tensor boards and there is a check mark here that is load pre-trained. So if you just run all, it will download pre-trained weights and it'll use those. But if you wanted to train your own, you can also just untick that box and then run all. I think if you want to periodically check your GPU. If you want to do that, I'm sure some folks here know, but doing a NVIDIA SMI. So I have a V100 here, but sometimes when you're connecting with public Colab, you might have access to Tesla T5s, P100s. And in order to successfully train, you want a P100 or above. I think for T5s, we tested it, and sometimes it does have memory leaks. So just letting folks know. Okay, so in the setup, we've got the simulator running. We also have several packages to kind of generate visualization. So that's what MoviePy is. And we also have notably all of the packages that are needed to run several models. The first being GPT-3, the Instruct series. So that's DaVinci 002. VIT-V32 for Clip. And that's a precondition to the next two models, Viled and Clipboard. Viled is a open vocabulary object detector. So they've got some, if you read their paper, they have some pretty cool examples of that. Literally, you can feed in a list of strings and it'll start to detect objects. Okay, and Clipboard is a clip conditioned transporter nets. So transporter nets, what that is a framework for pick and place. And what it does is that it captures a top-down view of the scene and then uses a sliding window as a way to figure out how to reorganize, or, first of all, figure out where to grasp. And then once it's grasped something, it's going to construct a crop around the local region of the crop region, treat that as a crop, and then slide it over the scene. So what this gives you is essentially a pick and place framework from the top-down view to help you decide, okay, where's the place that you should put something. And this is generally useful for robotics tasks like assembly, but kit assembly, or in all the other sorts of simplistic pick and place tasks. But all of this is trained from pixels to actions. And one thing that it lacks by itself is the ability to condition on language. So that's where Clipboard comes in. And what they do is they show that you can condition this model on clip text features. And so you can end up doing some pretty awesome demos where you're sort of asking the system to put the red blocks in the green bowl and sort of pack objects, sort things here and there. So it's very cool to see some of this stuff. So how these models kind of interact with each other is that you have something like GPT-3 processing human commands and turning it into a list of steps. And then it's only able to do this in context if it has, for example, a scene description, and that's being generated by Viled. Once it breaks down the steps, then it sends each of those steps into Clipboard, which since Clipboard can only do sort of one pick and place at a time, GPT-3 enables you to break it down into those individual steps, and then you can run transporter nets. Okay, so the jacks and the flags here for the learning side, what you're training is just mostly the Clipboard. And this is needed in the simulation world because at least in that domain, some of these models do need a fair bit of fine tuning to cover the real to sim gap. Cool. So following the setup, the environment code is here, and I'll quickly go over some of the things that you might see. Here there's global constants, and these are defining the set of objects that you would see inside the environment. In this constrained Colab, at least, there's only blocks and bowls potential some definitions for spatial locations, which is useful for your scripted demonstrator, which we'll talk about a little bit later, as a way to generate training data. But you're free to add your own objects. This is just regular PyBullet, so you can, if you have URDFs, you can go ahead and load that in. There's a gripper class, and this is specific to the robot arm. So unless you're really into the nitty gritty of how the robot gripper actually works, you can skip that. In the gym style environment, so in a lot of environments that roboticists like to play around, specifically for robot learning, like to use the gym-based API. And what that is that it's assuming you have a discrete time Markov decision process. So you have an agent that's interacting with the world and it's operating one time step after the other. And at each time step, the agent makes a decision, which is what action it should execute next. You put that into the environment simulates what would happen, and then ultimately you get some reward and some observation out of that. So this is, specifically the reward is useful for reinforcement learning, but if you don't have rewards, you can still study things like behavior cloning, learning from demonstrations, imitation learning. So the format of the environment is very much the format of these gym environments, which ultimately have APIs and functions that return observations when requested. There's a step function that ultimately takes into account action as input and then outputs the next observation. And then you have a policy, which is, for example, the one that's making the decision about where to pick and where to place. That is our policy in our case. So in here we have a particular gym style environment class. We also didn't strictly follow its gym style as opposed to strictly a gym environment, so that you can also modify your environment to your own desires. So a couple functions that I'll just quickly go over. During a reset function, this is going to instantiate a world, set gravity. This is going to add in a UR5, which is a robot arm. It's going to attach a gripper to the UR5 robot arm, and then it's going to add a bunch of objects randomly according to config, which is a parameter that just contains a dictionary of all the objects you want to load in. So you can preset that with respect to whatever random seed that you have. And then once it loads in all the objects, boom, the reset is done. Give it a couple steps so that the simulator sort of settles and all the objects sort of land on their feet. There's a couple functions in here. Another one too is the step functions. So that's one of the main gym functions that I talked about earlier. Feeding in the pick and place action, and then it's going to specifically and depending on your problem statement, your step function might do different things. So for example, if you're in a continuous control setting, your DT is going to be very small and your robot might only move a little bit each time step. Specifically in this environment, we call it sparse control, which is that it's literally executing an entire pick and place trajectory for each time step. So the decision making only happens in between each pick and place action. So this is particularly to this environment, it's particular to transporter nets and clipboard. But in the future, you can modify this however you want. The way to control robots, and Pete, if you want.
Yeah, I was going to say, do you want to, you have a servo J and move J function in there.
That's right.
So you could call out how it's actually quite close to like controlling the real UR5.
It is. So on the UR5, the way to control it is through joint commands. Up here, there's move P and servo J. Servo J, the description here, move the target joint positions with position control. Each arm, typically, you'll find either 6 degrees of freedom or 7 degrees of freedom. Usually the limits of those is moving between -2 pi to 2 pi, and really you're just controlling what's the configuration that the arm should be in now. There's also move P, which is specifically move the target and effector position. And this is running inverse kinematics as a way to give back what the joints should be, and then internally running a servo J to move the robot to that target configuration. So if you, for example, have a gripper and you're doing manipulation tasks, and oftentimes you're moving in this Cartesian coordinate space, X, Y, Z, then you can use move P as a way to move your gripper to wherever you want. As I mentioned earlier, you can set this to, you can be moving a lot in a time step, but you can also be moving very little in a time step, and that leads to continuous control type settings. Okay, do you have any other comments related to that?
A lot of the rest of it is handling rendering images.
Okay.
Yeah. Which you can talk through a little bit.
Okay. So the rest of this goes through how to render stuff. And I'm sure that many folks in this audience already knows how to do that. You want to set intrinsics, and you also want to set the pose of the camera. And there's two types of cameras that we're working with here. One is perspective, and that's just your regular typical camera, and physical camera at least. And then you have something more challenging, which is the, more challenging to build in the, actually it's possible to build in the real world, orthographic cameras, which are essentially these top-down views. Let me scroll down real quick and give you an example. These top-down views. Specifically in the context of robot learning, these top-down views are great because you don't have perspective distortion. So if you're running, for example, a fully convolutional network to make a dense prediction of where to grasp, you can be sure that your convolutional kernels will not be subject to the biases from learning over perspective distortions. And if you wanted to, each dense prediction at least has a very nice inherent bias that every pixel coordinate represents a fixed column of 3D space. For example, every pixel here represents around 2 millimeters, which is nice if you're doing planning, or if you're in the context of navigation, for example, a top-down view is quite nice in that setting too, to do shortest paths, etc. Really, this is just a proxy of a 3D representation that we would typically want. But the way to get this is we would take an RGBD camera, and it has to be calibrated so you know the pose, project it into point clouds, and then re-render from this orthographic viewpoint. So oftentimes you might get artifacts with spotchy dots here. But then if you wanted to get a perfect orthographic view, you can do that in simulation, but generally getting these types of views is harder, or you need to have some particular setup. Okay, so that's most of the environment code. Yeah, and essentially to initialize an environment, you want to define what are the objects that exist in the environment. You can set your random seeds, arrange the objects, and it'll randomly arrange the objects with respect to the seed. Before moving on, are there any questions so far in the audience? Any questions on Zoom?
There's some questions on Zoom, yeah.
Servo J contain R. Yeah, that's a good question. Servo J is just the joint configurations. So each degree of freedom, which is, for example, an elbow, really only has 1 degree of freedom. The orientation, which is, if you want to control the orientation, you can do that with move P. So I believe the code has an example of that. Oh, turns out it doesn't. Oh, okay, I see. Okay, so if you want to control your own orientation, you can, but you want to set the quaternion, which is target quaternion here, parameter. Here we have it fixed to be always top down, but you can definitely change that to something else.
Good question.
Yeah, good question. Any? Any other questions?
Hi.
Yeah.
So do I understand correctly that if you give the target coordinates to the pipelet, then it will handle the path planning?
So it'll tell you the target joints, but then the actual path planning of like dodging obstacles, it might not. So with just a simple PD control where it closes the loop so that it goes to the target joints, yeah, that's already taken care of. So that specific command is set joint motor control array. So that actively moves your robot to the target joint position. But if you have obstacles in the way, it won't be able to handle that.
So which part of the pipeline is handling the obstacle avoidance?
That'll be in between sort of these lines of code. So if you wanted to have it be aware of obstacles, then within this function here, servo J, you can have it take into account additional information so that.
This one doesn't do it.
This one doesn't do it.
Okay. Thank you.
Okay, moving on. Does the simulator take singularities into account?
Also, sorry.
Yeah.
Can you speak a little bit louder?
Yes. So does the simulation take singularities into account? It does not. So specifically with the inverse kinematic solvers, here it uses cyclical coordinate descent, which means that it's an optimization-based algorithm. So you have an initialization of the joint pose, and then it's going to compute gradients on that joint pose as a way to iteratively move to your target joints. So you do have some inverse kinematic solvers that are not optimization-based. Those would be analytical ones. These ones would tend to fall into singularities where you need to have some way in order to strictly handle those. But the PyBullet inverse kinematic doesn't, but it does require you to have a good initialization in the beginning. So if you're constantly moving your robot smoothly throughout 3D space, then it's usually okay for most purposes. But if you're jumping to a very far position, then the robot might not give you a solution that you originally intended it. So it's good to keep in mind that if you want to, for example, if the robot had one particular pose on one side of the workspace, and then you wanted to move it to the opposite side of the workspace, if you see that in transition of moving over, the robot sort of flips its elbow upside down, that's because the optimization didn't find a plan that was at least keeping the elbow up. The shortest path didn't necessarily get to that. So you want to add additional waypoints in between so that you can keep the arm elbow up. That's a specific thing for path planning. Do you also want to add?
add a couple things.
Okay.
To add a couple things, and there's been some good questions. So I think one thing that's helpful to keep in mind is, like, there's good questions about, like, oh, is this doing obstacle avoidance, and oh, or like you gracefully handling singularities, and you know, robotics is very hard. So I think whenever you can kind of like ignore certain problems and focus on other ones, it's very helpful. So like, there's actually a ton of robot demos that you'll see, and you might think like, oh, that robot probably can do everything, but actually it basically can't do anything that it's not showing you often. And so there's a lot of robot learning research that happens where you have a robot sitting next to a table and it can't handle obstacles. And like everybody knows that we could engineer it to handle obstacles, but then that might be like, actually obstacle avoidance and path planning is its entire own like massive subfield with many decades of research and very challenging. So if we were to add in obstacle avoidance here, it could potentially double, if not more, the size of this Colab. And so it's just helpful to sort of like, you know, when certain things can be studied in isolation, it's helpful. And then another thing that I wanted to call out too is, Andy was walking through kind of how the simulator is set up. I think it's a really nice, like, you know, easy to play with simulation setup. One thing to call out as well is like the actual choice of what are we simulating and like what are the objects and like, what does the scene and the environment look like and what can we do with that? I think that's a really interesting question. I'll cover some of that more in my talk later. And here, you know, it's pretty simple. We got a robot sitting next to a table, got some blocks, got some bowls. And importantly, some of the blocks are color different than other blocks, and some of the bowls are also color different. And you'll see later, as simple as this is, just a few blocks and a few bowls with different colors, it's sort of a really nice level of complexity where it's complex enough to actually do some really cool, like language conditioned pick and place tasks, which we'll get to later. But it's also not, you know, too much. We're not doing some like, you know, GTA 5, you know, triple platinum video game environment. So I just wanted to call out those two things.
Cool, thanks, Pete. All right, so moving on. The next part of the Colab hops into running Bild, and a lot of this code comes from the Bild code base itself. So you can go ahead and take a look at their paper as well as their GitHub links if you want to learn more about their code. But specifically, how this is being used is to generate, convert from an image to a list of objects that we would see in the scene. And this is helpful for providing language-based context to the planner. So this whole section here of demo Bild sort of just goes through that, loads a Bild demo, downloads, runs forward passes. You might want to play around with this hyperparameters in case you need to set the object detector in a specific way. But ultimately, we're using it here just to you know, discover where the yellow bowl is, the green bowl is, and the blocks are. And we're not taking into account the spatial information currently. We're just formulating this list here. Later downstream, we'll have a robot policy be able to figure out where it should grasp or where it should pick in place. So the spatial information actually gets tossed out the window. So we're really only using it for object recognition currently. We have here a scripted expert. I guess a lot of paper terminology uses this term scripted, which is just means that somebody hard-coded a couple heuristics or maybe even potentially writing some complex algorithm behind it. But ultimately, it's manually engineered. And what we mean by scripted expert is that this is a Oracle system that is able to execute pick and places. And you can use it to collect demonstration data. And there are, at least in the context of learning from demonstrations, if you're studying it inside of a simulation environment, there are various different ways to get those demonstrations. You could either use a scripted expert, which has access to the ground truth poses of the object so that you can pre-compute where you want to pick and place. But you can also, for example, and very good work from, for example, NVIDIA's lab, where you can have a person hand track their hands, or maybe even using teleoperation tools to try to control the robot, and whether it be it in real life or in sim, you can have move the robot to do various tasks. And that's one way to get expert demonstration. And another way to get expert demonstrations too is training an RL agent to solve the task first. And then depending on the seed, you might have good expert demonstrators, maybe medium demonstrations. You can use all the trajectories that they come up with as a way to provide expert demonstration data. But yeah, in the context of this Colab, we're just using a scripted one that uses the ground truth state. This is access to privileged information. So this is only for generating training data. Later on, the policy that trains off of this does not have access to this information. The dataset section, you can either, there's a check mark here for load pre-generated. We did pre-generate a dataset of 10,000 pick and place examples. So that when you run all with this checked, it'll download it by default. But if you uncheck this, then you can generate your own too. So just to give a quick example, we'll uncheck this. So it'll generate a random instruction, pick the green block and place it on the yellow bowl. And then the simulator will run. The video recorder will record what the simulator saw and then output it inside the Colab notebook. So you'll see the robot executing this. Yeah, so specifically here, I chose to generate 2, so that's why you're seeing 2 videos here. And every now and then, while you're generating training data, you want to reset the environment with new objects, new goals, etc. And it's funny because resets in simulation are so simple, you can just code it up. But in the real world, they take a lot of manpower. You got to have somebody who's next to a robot all the time, wrangling, resetting objects and trying to move them in similar places. So anyways, in simulation, it's quite nice to have this, and you can literally also debug with it too, because if you set the random seeds, then you can control it to however you desire. Cool. So the information that gets saved whenever it executes a pick and place action is the pixel location for which the pick was executed and the pixel location for the place, as well as the textual command that was received as input. Okay. So there's here we have a section on model, and all of this is, by the way, I also want to call out that we'll be talking about limitations of the stack too later in the talk. So if you're interested in what are interesting research questions that people can tackle using this Colab, then I think we'll go over that a little bit later. But for now, in the meantime, we'll just sort of go through the rest of this Colab. Any questions so far? Yeah.
So, could you explain a little bit how did you generate that navigation as well?
How I generate the...
How did you get that data set of 10K demonstration?
Yeah. The question was, how did I get the 10K demonstrations? That was on a local PC and just running it for a couple hours. You could also do the same here in this Colab too. So if you go ahead and up here, so uncheck the load pre-generated and then set your data set size to 999. And yeah, you'll get the similar data set. In general, something like clipport, which takes into account the textual command and outputs the pick and place, if you want to generate, the more data that you have access to, the better the model becomes. So 999 was just on a whim. We wanted to generate enough data in an afternoon, but you can increase this to 100,000 and I'm sure it'll be better. Okay. In the model side, we have an architecture that is, so I guess to provide some context, there's a bunch of con blocks here, but let's just go into the paper for transporter nets so that we can go over what the pipeline is really doing to do pick and place. Okay, so the key thing to look at is this diagram. So suppose that you have a system and you wanted to put the block and reorient it into the correct spot here in the fixture. Specifically, what the pipeline does is it takes this top-down view and it feeds it into a fully convolutional network to compute dense features. And we visualize the dense feature here. And this is specifically, right before this, we also have a similar network architecture to this first part here that predicts a picking location, or how the system would grasp the object. And suppose that it predicted the center of the object. So what the transporter networks does is it crops out this local region in the input image. It, for example, rotates it in various different angles and feeds it into another fully convolutional network to generate dense features. And then you apply a cross-conv on the crop over the placing features. This is in a sliding window style fashion. So ideally, the object that's correctly oriented on top of the fixture sort of generates the highest cross-convolutional values. And ultimately, you generate this single image plane of logits, and you can match that against a one-hot pixel map with cross-entropy. So there's a lot of nice benefits to this in the sense that there's interesting nuances in the sense that when you're doing robot pick and place, for every possible input image that you have, you only have one action that was really executed by the robot. So if you were learning from demonstrations, you really only have one pixel. But what's interesting is that if you have a lot of training data, you can actually get these things to also reflect multimodal distributions, which is what we're really after. So a couple examples. For example, you can have picking locations that are located all around a disk. And it's pretty cool to see that picking spots would generally be highlighted around the disk. And this is just this is also, there's a couple things at play here, but another thing that, one part is particularly the loss function, but another part is that there's inductive biases that are at play. Because this is a fully convolutional network, then you have this spatial prior. So for example, here it's likely using red pixels, for example, as a way to figure out that that's all the pixels that belong to the object. So this is good for grasping because all of those are valid grasps with a suction cup gripper. And here, this just shows that if you, for example, at least with transporter nets, if your pick condition placing, let's see if I can find a better visualization somewhere. Okay. So what this shows is that, say that the task was to take the E shape block and put it into two target E shapes. The loss function can correctly encourage two spots that you need to place the object at. So that's just a byproduct of both the loss function and the spatial biases. Similarly, if you are, it's subtle, but if you grasp an object that's off center, for example, on the edge of this disk, then the way that you place it actually needs to be sort of different each time. You kind of have to orient it correctly and also translate it respectively so that it's against the edges of the whole of the kit here. And what we're showing here is that across all the rotations, if you take all the heat maps and you collapse it, you form this donut shape. But if you expand it back up and you imagine that it's sort of 2D heat maps with a rotation at every layer, then it forms a spiral in that 3D heat map in SE2. So that's just to show that these systems are pretty good at learning multimodal distributions. And I think that in general, robot actions, there are always so many different ways to do the same thing. And making sure that our policies can reflect multimodality is actually very important for robot learning. Okay, so that was a quick spiel about the transporter nets architecture. And what clipboard does is that it broadcasts the clip features of the text and brings that into all of the layers inside transporter nets. And that's exactly what we try to do here, and we try to train it over time. One thing to note here is that this architecture that we have in the Colab here is similar to clipboard, but not exactly the one that clipboard has. Yeah, just a heads up. So there's tensor boards to sort of track training over time. And if you want to train your own model, then you just untick this, and then it'll run through. It'll generate batches of 8, and it actually requires quite a bit of memory to train. So batch sizes are not very large. So here is a demo of a trained clipboard. So we already have that loaded in memory. So yeah, this is a test variant of clipboard, text condition translation only transporter nets. Text must generally be in the form, pick the object and place it on location. Admissible objects are the objects that you've defined up in the top of the config, and also the objects that have already been trained in the training set. And admissible locations. So at least in the simulator, the scripted demonstrators also have done things like put the block in the middle, or put the block on the side, put the block on the corners. So that's to the extent that the placing locations are also spatial locations. So there's some training data for that in here too. Yeah, so ultimately you can define and reset the environment, and then you can ask it to execute some of the things that it's seen before. So this is a testing scene. And the system will execute the pick and place, and then it'll try to generate a bunch of visualizations so that you know what's happening. First and foremost is generating what the robot thinks it did. That's executing a pick here and then a place here. The picking heat map and the placing heat map as outputted by transporter nets, and then executing the actual actions and a before and after image. So we can, without resetting, we can subsequently ask it to put the green block, place it on the green ball. And note that the text instructions have to generally be of the form, pick the blank and place it on the blank. And that's just because that's what clipboard has been trained on. Yeah, so it executed the correct pick and place action. And now let's put the blue block and place it on the left side. Cool. So it looks like it did that. All right. I guess, yeah.
Would be to call out like what it can't do yet.
Yes.
Because we have like 4 minutes till coffee break.
Yeah.
And then we could suggest people to train their clipboard models if they want.
Okay.
And then we could do more on like the LLM and stuff at the end.
Sounds
Would
good.
be one option.
Yeah. All right. Things that it can't do. Great suggestion. Pick the blue block and place it on the.
Or like undo. Or like
On top of another block?
Yeah, on top of another block works.
but undo the last step.
Yeah, undo the last step is definitely not going to work. So undo the last step, and this is with clipboard only, so it's not using a GPT-3 to translate commands into things that clipboard knows. So if you just straight up fed the text, the model can take it in as input, but it won't know how to undo. So yeah, it's just picking out the yellow block, I guess. If you also decide to put in words that it doesn't know, like
this step too.
oh yeah,
You like sort all the blocks.
that's true. Yeah, so just out of the hard constraint that it can only execute one pick in place from the textual action, sort all the blocks without GPT-3 is not going to work. Unless maybe you've trained Clipboard to actually recognize that command, but that might take extra data generation. Yeah, so it's just stacking blocks, which is not what we want. Okay, so these are things that Clipboard on its own cannot do. And later we'll get into why combining it with language models, VLMs, and policies can get it to work, do some of the undo and sorting tasks. And then for now, if you want, since we're going to have a sequence of talks throughout the rest of the tutorial, you can also go ahead and train your own model too. It'll take a couple hours, but hopefully by the time that we're done with the get to the point where we're going to talk about the language model stuff, then you can ideally be able to run with your own trained model. Yeah, so I think we can let you go on your coffee breaks.
Do questions too.
Yes, and questions. Any additional questions from the crowd? Yeah.
I haven't used Colab before, so how much of this tutorial is tied to Colab, and can you run this tutorial locally on GPUs?
That's a great question. The question was, how much of this tutorial is inside Colab? You can copy paste this entire thing into your own Python script and just run it on a local machine with a GPU, and it should work as well. Yeah. And I think that you can also use this in the style of Jupyter Notebook. So up here, if you say that instead of connecting to a hosted runtime, you connect to a local runtime, then that's essentially doing Jupyter Notebook. And that's how the video was recorded. Any other questions? Okay, cool. So we'll see you back after the coffee break in 15 minutes.
I just want to show the schedule.
Yes.
Is it this one? No? This one?
Oh, yeah.
Did you try to pause it? Did you pause it?
Oh, we can. The mic button is here.
This meeting is being recorded.
Okay. Okay. Everyone can hear me here. Can we just check that it's streaming online? It looks like it. Yeah, cool. Okay, great. Thanks everyone for coming back, and we're excited to keep going here. So my name is Steve Florence. I want to talk today about a toolkit for vision-based robot learning research. So what do I mean by a toolkit for vision-based robot learning research? The question that I'm putting forward here, and I'm going to try and take one shot on the answer with, is what are the essential tools for doing research in vision-based robot learning? And I'm going to try to connect some of these ideas back to the Colab that we've been looking at today. For the experts in the room, I'm genuinely curious, maybe you already know all these things, but in terms of the way that I'm going to try and put together, what is kind of the short list and what's the relative emphasis on different things? I'm curious maybe to chat after, and how does your perspective compare? And for the newcomers in the room, hopefully this can help get you started in doing research in the area. So doing research in vision-based robot learning, I think what the majority of the emphasis is often about is with the methods. So, the reinforcement learnings, the imitation learnings, the self-supervised learnings, or just prompting the LLM to solve everything, whatever it is, whatever the method is that you use. These are the things that I think we talk about a lot. And there's all this other stuff, which all come together as tools, which are sort of agnostic to the methods themselves, but I think are incredibly important in sort of actually making robot learning research work. They're sort of the behind the scenes heroes here of robot learning research. Things like understanding real robot challenges, collecting data, environments, and tasks, things like that, things that are agnostic to the methods. And I think it's the methods that, they often get a lot of the glory, and they're the words and the titles and abstracts of research papers, and they're covered ad nauseum in your formulation and method sections, and they're the key ideas that we talk about. But it's often the tools, I think, that inform us, why do the titles and the key ideas matter? They also explain the reasons why things can come together so quickly out of productive groups of people. And they power the experimentation that shows that things work. So this talk is going to be about the tools. And for those of you that know The Wizard of Oz, I sort of feel like it's like, the man behind the curtain here. So I think this is actually pretty common, so not so uncommon, that you might end up in this situation where, and this is just a little bit more motivation here, your algorithm might end up being 10 to 100 lines of code, maybe in that range. It's fine if your algorithm is more, but it's legitimately a thing I see often where people's algorithm is tiny. But then your everything else could be orders of magnitude more, 10,000 lines of code, whatever it is. And I actually think this is totally true for the Colab we're looking at today in terms of, kind of at the end there, which was kind of the contribution of a thing that Andy and I and others worked on recently, was just kind of wiring a few things together. And, there's not that many lines of code, but the rest of it, that's like a 2,000 line Colab notebook. So yeah, what is this everything else? Evaluation code, data set processing, sim environments, these types of things. Another thing that I think is not so uncommon, especially I think for vision researchers, and if you haven't run into this, this is especially for you. And if you have run into this, well, I don't know, maybe you'll get a laugh out of it. But I feel like I often have this situation where I'll text a friend or a colleague, in some other lab, and I'm like, hey, cool paper. I just saw it, go out on the internet, pretty cool stuff. And they'll say, thanks, yeah, we're pretty excited about it. It's like a simple but powerful idea, talking about the method. And then so you think to yourself like, yeah, cool. But then you're thinking to yourself and you're not sure how to say it, but you're like, man, it just seems like so much work, and you're not envious of all the evaluations that they ran. And so you're maybe you're a little passive aggressive and you're like, it must have taken forever to run all those experiments. Bravo, seems like a lot of work. But then if you've never run into this type of comment before, I think it's very helpful to know that this exists. That sometimes when things look like a lot of work, they was actually very quick to iterate on because they had everything else set up. So, something like, I feel like it's often said, oh, well, we already had all the evaluation harness set up. We just started working on the idea a couple weeks ago. So I think it's how that highlights the importance of tools. So what's an analog in computer vision? What might a toolkit for machine learning in computer vision look like? Just a few ideas, access to data sets, evaluation harnesses that we were just talking about, maybe tools to label your own data, visualization tools, these types of things, just as an analog. In vision-based robot learning research, this is kind of the toolkit that I'm going to talk through today. Relative emphasis on different things. So, real robot opportunities and limitations, the big picture challenges in robotics, environments and tasks, data. It's kind of a niche, but I think it's really important, parameterizing observations and actions and bringing it back to real robots. A balancing act that I want to call out that I'm going to be trying to do here is, on the one hand, real robots are sort of ultimately, I think, the thing that as robot researchers, as roboticists, we should care about. I think they should motivate our problems. They should sort of, the robots working should be our sort of final actual metric and evaluation. But on the other hand, as many of you may know, sort of simulating robots is very helpful for evaluating a large amount of things, getting high throughput metrics, things like that. But there's another related but different balancing act I want to call out as we walk through this sort of toolkit I put together is, on the one hand, having access to real robots and actually running real robots is very important, but there's a certain amount of resources that are required to be able to do that. And on the other hand, to the extent that we can frame problems in terms of being approachable via just simulation, then we can be in this place where anyone can contribute to advancing robot research, which I just think is awesome in terms of letting anybody in the world, some kid, I don't know, halfway across the world, where you only need an internet connection and a Colab to contribute. So when possible, I'm going to try and phrase things in terms of, hey, look, you could do this sort of thing just with an internet connection and a Colab, or you don't need to use Colab, but it's just a simple, easy example and gives you access to free compute resources. But also, sometimes we do have to ground things back in real robots. Okay, so real robot opportunities and limitations. The real meta question here is, this is sort of the question of how do you choose what to do research on? And the question is, what mountain do you want to go climb? What do you want to go do research on? And when you're wandering through the forest and you've got topic 1 and topic 2, and your advisor wants to work on topic 1, but you're like, I don't know, topic 2, how do you choose what to work on? This is like one of the key things in research, and applies across everywhere. But I think it's especially interesting to think about in robot research. I think one framework that I think is very helpful, doesn't cover everything, but I think it's a very helpful framework. At the link at the bottom there, this is from a blog post by John Schulman, and puts out that framework of idea-driven versus goal-driven ways of choosing what to do research on. And John actually himself did robotics, at least at the start of his PhD. And so I think part of this sort of framework is inspired directly from working on robot learning research. So just to define what these things are, idea-driven is, you have some hammer, you have some method, you have some algorithm or some cool little trick idea, and you want to go apply it to something and see if it's useful and write a paper about it. That's kind of idea-driven. On the other hand, goal-driven is you just want to go accomplish something. With a robot, it's you want to go accomplish something with a robot. And maybe you don't care at all how it happens, and you're just excited about the goal that you're going after. And maybe when you share that result out, if you're successful in the end, nobody's going to care that you use some simple method to make it happen because the result is quite impressive. Or maybe you need to innovate and come up with a whole bunch of new things. So idea-driven is a little bit more sort of, you've got the hammer and you're looking for nails. Goal-driven is a little bit more, okay, what are the nails? What are the problems? What are the opportunities? And in the robot learning case, I think it's especially interesting to think about. But we can't just say, oh, let's go for the nails. Let's go for goal-driven. I think we have to have a sense of, what goals are worthwhile and how are they grounded, connected to impacting the future of robotics. So it's very simple, but I think often one of the best ways to start and even come back to often is just asking yourself, sort of, use your own imagination. What impactful, fun, exciting, interesting, valuable, choose your own objective function, thing do you want a robot to do? And I think it's just, it's easy to get lost in the weeds of, oh, I'm doing this, working on this little problem, but what do you want the robot to do? It's a very helpful question. And a little checklist to go through is, okay, do easy alternatives work? Is it implementable in the real world? Or is there a path to do so? And it might be kind of hard. Doing anything with robots is pretty hard. So is it an interesting enough goal that it's going to be worth your N amount of time, energy, focus, and dollars? And if the answer to the questions, all those are yes, then you might have a worthwhile problem. On the limitation side, what are things that real robots currently struggle with or can't address? I think for people maybe new to robotics, especially because I love sci-fi, but it's funny because I'm a robotics researcher, but I don't know how old I was when I realized that C-3PO was a man in a costume. You know what I mean? I was I don't know exactly what the number was, but it was at least double digits probably. Let's put it that way. But so getting a sense of what is actually the state of what robots can and can't do, I think is really important to do. And I think the most successful and easy way to do it is just to watch a lot of videos of real robots. And that comes in a bunch of different flavors. Whenever you see research papers and they have video, just click on the video. It's the first thing that I always do. I feel like a lot of researchers, and probably Envision too, just always looking for the video is the highest bandwidth way often to understand what's really happening. And then also too, just search the web. just watch a lot of videos of real robots. I think that's honestly the best way to just build a lot of intuition of what is actually possible and not. And pay attention not just to what you see them do, but also pay attention to what do you not see robots do. I think I mentioned this earlier when we were chatting with Andy, that often when people put together robot demos, they kind of show you everything that the thing can do. And if they're not doing something, then you know that probably can't do that. Or look and try and take note, like what types of regularities or assumptions seem present in the environment or the setup at large. And what do you know, hopefully they, in research papers at least, they'll actually show some failures and, take note of those too, of course. I think another huge source of knowledge to look at, especially for folks into robotics, is learning from real robot competitions. So I think DARPA gets a lot of credit for, it should get a lot of credit in my mind for running and organizing and instigating a lot of these things over the years. So there was like the DARPA Grand Challenges, which was sort of a key step in building a lot of momentum in autonomous driving. There was the DARPA Robotics Challenges, which is the humanoids, like Atlas and a bunch of other humanoids. That was a huge program, 2012 to 2015. 2016 maybe too. These are rough dates. The Amazon Robotics Challenges, Andy participated in that one. Props to Amazon for actually putting that one together. Most of my list here is from DARPA, but I think it was awesome and really well received by the community that Amazon put that one together. Or I think the most recent one in the DARPA world is the Subterranean Challenge. So there's just a ton of learning to be had from these types of events as people are actually trying to put forward on real robots and competitive teams and sort of problems that by definition robots can't easily solve, like recipes that actually work. So definitely with these, I recommend watching the videos, reading the recaps. There's all these like review papers of how these things went down and trying to take note of what worked well and why. And if another one of these sort of opportunities come around, I would strongly encourage participating if you can. Another one too, you might be humbled. Keep note of what robotics industry has already solved. There's just a lot of things that, if you can, I recommend going to a robotics industry conference. There's a lot of things that like you might be like, oh no, my research problem looks very similar to that, but they're just deploying it and like doing all these things at scale in industry. So that's another one to keep in mind. And if you do have access to a real robot, I highly recommend just trying to see how far simple and standard techniques will take you, and that can help you identify what are the sort of limitations that maybe learning-based robotics or new techniques actually need to come in and solve. So next in the toolkit, just keeping in mind big picture challenges in robot learning. So these are the big picture challenges. This though is just my own biased and non-comprehensive shortlist. And I'm going to show you what maybe mine is at the moment, just a quick take on it. But definitely I encourage you to make your own and sort of accumulate your own version over time. So I would say my number one is just it's very hard to get tons of data. You want to do learning, sort of by definition, you kind of need data. In robotics, we can get a good amount of data, but it's very hard to get a ton of data. And I think that is one of the fundamental challenges of the field. And I put it as a separate item. Number two here is just exacerbating number one, which is that number one is exacerbated by the embodiment across task space explosion of the sort of space over which the data needs to exist. So what I mean by this is that in computer vision, I know there's like point clouds and other things, but let's say that a large majority of computer vision operates on like the RGB image, or maybe it's monochrome, whatever. But you have RGB images, and there's a lot of different cameras out there, but you know what, as you all know, there's a lot of regularity in what an RGB image looks like. Height by width by 3, it's a beautiful thing. There's a lot of regularity. And what this means is, of course, there's different intrinsics, there's things that affect different things there. Exposure, I know there's a lot of subtleties, but it's just known that RGB images from all over the place is sort of, as long as they're sort of not too fisheye and don't have other weird artifacts, we can get machine vision systems to work at scale on a lot of these things. Everybody has one in their pocket. They all have roughly the same sort of representation of the data. In robotics, it's completely different. Every robot, especially from the actuation side, has a different embodiment. And even if you have like 10 copies of the quote unquote same robot, every single physical actuator, maybe ages a little bit differently, maybe somebody replaces something, so the actual geometry of it is slightly different. And that's even if you have 10 copies of the same robot, but there's all these other robots out there. And so sharing data across all these different robots, this embodiment challenge of how they have different embodiments, it just completely explodes the amount of data that you might want. So maybe you want to have enough data to cover every single imaginable embodiment ever possible, but that it just explodes your data requirements. And on the other side, in conjunction with the embodiment challenge, is the task specification challenge, which is that, in computer vision, there's actually a fair amount of diversity of different tasks, so you might have classification, detection, pixelized segmentation, whatever it is. In robotics, though, it's just endless. So there's so many continuous spaces over which task specification might exist. So a task might be, hey robot, can you take this coffee cup here, and can you take off the lid, and can you put the lid there, and can you put the cup back there, and actually first, can you pour out maybe 50 milliliters into another cup, and like all those, like that's a valid thing to ask of a robot. It's I think language has a little bit more of a similarity in that the sort of things that you can ask a language model is sort of unbounded other than just what's expressible in language. I think we have that same challenge too in robotics, but again compounded with embodiment. So I think this is my number 2, and it just exacerbates number 1. Data's hard. Okay, number 3, related but different, is it's just hard to evaluate large N in the real world. I think we can do things in the real world, but it's hard to evaluate a ton of things in the real world. I have a few thoughts on sort of my current favorite recipe to try to combat this, which is that you start with motivating from real world opportunities and limitations, and then you make a relevant simulation. This is a common technique that I think is often useful, and use the sim to compare like your full set of different ideas. And then cull that full set of different ideas down to some small subset and validate and compare those things in the real world. I think this is sort of a very practical, my current favorite recipe for trying to address this problem, but it is certainly very open for research on how to do good real world evaluation. And I also just want to note that you might look at that and be like, oh yeah, sim to real. And I think sim to real is interesting, but the recipe that I'm saying here is sort of not sim to real of like a model itself, but rather it's kind of like meta sim to real, where you evaluate lots of different things in sim, and then you choose the best sort of algorithms or maybe hyperparameters and just separately entirely set them up in real. It's kind of like sim to real of the algorithms, but not the weights, so to speak. And again, a lot of people use this type of recipe, but it's sort of my personal favorite. Okay, so that was some thoughts on big picture challenges. Again, I encourage you to come up with your own recipe. So let's talk about evaluation. In robotics, I think evaluation often boils down to, in sim or in real, setting up environments and tasks. And I think there's a lot of subtleties here. And especially here with computer vision folks, robust and mature evaluation tools, more comprehensive, widely adopted, et cetera, is something that in robotics robotic researchers would love to get additional help from computer vision, because I think over the past decade or so or more, robotics has been over here looking at computer vision being like, wow, there's been so much consolidation and high quality data and benchmarks and the quantitative focus, and that has really driven a lot of great innovation in the field. And in robotics, I think we have some progress in that direction, but certainly more work to do. So let's talk about metrics. So with robots, I would argue that the metric the robotics field should care about the most is a very simple one, and it's % success. That's my favorite metric. And there's a reason for that, because it's at the end of the day, if we care about making robots work, why don't we measure whether or not the robot works? That's sort of the metric at the end of the day. Of course, it's more subtle than that. It's % success over some distribution of scenarios. How often does the robot work? That is the question. Especially for things that might not have been possible before, or does it work better in a wider variety of scenarios, some wider distribution compared to prior alternatives. I think arguably there's a whole bunch of other metrics that you might care about, and we measure and we put in research papers, whatever it is, we track for projects that we're developing. I think they can all be very useful. Ultimately, it's at least useful to consider thinking about them all as just proxy metrics for % success of real robots. I would say. I think % success it can be sort of phrased to kind of fit whatever problem you care about. That said, though, I think it is really hard to capture all qualitative robot behavior in quantitative metrics. And I think there's basically just no way around it. I think that having videos, I already talked about videos once, having videos of robots actually doing things just communicates so much qualitative nature of how the robot is functioning that's really hard to capture with quantitative metrics. So the combination of percent success, maybe other metrics if you need them, and videos, I think is kind of the best mix. I think there's an interesting debate. I couldn't find the reference, but I remember reading the paper. I think it was maybe Peter Court, I forget who it was, but an interesting sort of question that like, oh, maybe what robotics research needs as a field is less robot demo videos and more tables with bold numbers. And you know, CVPR, everybody here is really good at tables with bold numbers. I think arguably my personal view is that I think we need both in robotics. I think tables with bold numbers are really good and they do drive sort of like, okay, let's actually be honest and what things are working the best. But I think again, there's just so much closed loop, real world interaction, things that are hard to capture with just quantitative. I think we need both. Okay, so the art and science of environment and task selection. I think there's, some of it is definitely art. Some of it can maybe be more science, but I think there's really a lot here where the question is what makes for good tasks to be working on in robotics, or tasks to be trying to apply our methods to in robotics. So I think the best way to do this is maybe through some examples. So I'm going to be biased and pull some tasks from some of our own papers over the years. But this is one on the right, which is the hang the mug on the rack task, which is actually over just the past couple of years been adopted in a few other papers I see. But I think it's a really nice task to get a robot to do. And I'll walk through a few different reasons why. The first one, which I think applies to all tasks in general, no matter, because you know, different tasks will have different flavors, measure different things. But one thing that I think is really important is it should be very visually clear and sort of like satisfying, maybe even like sort of ASMR style, of you know, whether or not success happened. A bad task to be studying in robot learning research, I think, is where you see the robot do its thing, and at the end of the little segment of the video, the title says success, and you go, really? You know, you want it to be obvious that the thing succeeded. And I think like hanging a mug on a rack is great, because if it hangs on there by itself, it's obvious that thing worked. If it doesn't, it didn't work. So I love that aspect of it. And again, I think it's really just a nice thing to have, at least in research, for a bunch of different things. This one is particular to this task. It might be something that you care about. This task requires precision to get the, you know, the actual handle of the mug onto the rack. It's naturally a very sixed off task. Actually, a lot of tasks can kind of be more maybe just translation only, or maybe just kind of top down. This one is very full 6 degree of freedom in its nature, so that's nice about this one if you care about that. It is a single rigid object with a single rigid target, just to call that out. You know, maybe you care about deformable objects or liquids or other things like that. And another one that I think is nice about this one is it lends itself very well to class level generalization, which is, if you're interested in studying that type of a topic, it's a good setup for that. Let's look at another task, another one that I like a lot, which is from a paper of ours from last year, which is sorting the blue blocks from the yellow blocks, or sorting in general of sort of like, you know, 8 things is a lot more than one thing. And so in this task, yeah, the robot's goal is to sort all the yellows from the blues. Again, I think this one is very sort of visually clear and satisfying whether or not success happened. Maybe initially at the very first frame of this video, you weren't sure what was going to happen, but by now you can kind of autocomplete in your head. Well, you know, what should happen? Another aspect of this one is it's a handful of objects, not just one, all with desired configurations. I sort of talked about that, but that's, you know, different than the one we looked at before. One interesting thing about this one is that we trained it so that the ordering doesn't matter. So it really forces a huge amount of multimodality. So at any point, you know, oh, should I do this block first or that block first, et cetera. It's something that's super easy for humans to think about, but can be actually hard to train robots to do. And then another one is, for those of you that are maybe not familiar, this sort of taking a single point of contact pusher and sliding things around on a table is actually a very commonly studied problem in robotics. And yes, we know that we can just go grab the block and move it with an enveloping grasp, and it's much easier. But the act of choosing to just touch it with a single point of contact forces you to have a lot of feedback, because it's very hard to predict with a single point of contact where the thing's going to slide. And so it's just a good, simple way to force yourself to deal with high rate feedback in this case is a thing to study. So that's that task. So those are maybe, those are just a couple examples. But another thing too, in addition to sort of thinking about, oh, how might I sort of maybe set up my own tasks, is we were talking about, computer vision is great at benchmarking. I think it'll be good for the field to coalesce more and more towards standard benchmark tasks. And I think it's really helpful to sort of take note of what's out there already, and appreciate what's really nice about some of the things that are out there already, but then also, keep in mind, what might you want to improve? And I think actually one thing that happens a lot in robotics benchmarks and things like that is that people love to complain. And I get it. It can be easy to sort of get in the like, oh, this data set, it's not very good because it misses that or misses that. But I would encourage you, rather than playing that game too much, just get out there and help make it better. And actually, once you start to try to make it better, you'll realize, oh wow, there's actually some really cool things about some of these data sets already. So this it's a really nice task, these droid tasks, which are included in the D4RL suite, but from a different paper from before, but nicely included in the suite. They have some really nice sort of like high degree of freedom hands interacting with environments. This one's opening the door. This is from the Ravens benchmark, which was from the transporter nets paper that Andy was talking about. This is just one of the tasks there. There's a handful of others listed on the left. I encourage you to not just sort of like read the papers, but actually dig through the sim code for the standard tasks. And when you are running methods on these tasks, I highly recommend, it's surprising how many people don't do this, but it's really helpful to actually render it and qualitatively watch videos of what's happening. Don't just look at numbers. Okay, so another key question I think to keep track of with tasks is what type of task conditioning is present. We were talking about the task conditioning with, hey, robot, can you move this cup here? It's, it's sort of language models are sort of an analog of have a huge amount of conditioning. Within robotics, when we have tasks, yeah, there's a variety of ways to condition them. So they could be sort of like object state, like maybe pose condition or image condition, goal image condition, or task ID condition, or maybe language is a very flexible way to do it. It's helpful to keep in mind. Actually, the task that I showed on the previous page had conditioning in terms of like goal configurations of objects, but they didn't have a goal image. It was just sort of trained to sort of mimic the demonstrations was the only way that was conditioned. I think it's really interesting to think about the sort of like, crank it up to kind of like the DALL-E or image, these sort of like very flexible, just text to image generation models, like would be the analog for robotics, where we just have super diverse natural language conditioned tasks. I think that's a really nice place to be shooting for. Andy talked about Clipboard, and it's in the Colab. They're not all the way there, but I think they put together a nice suite, which is actually built on Ravens from the last slide that I mentioned, of having a pretty good diversity of language conditioned tasks, and I think that's a good step in that direction. There's other works that also have these types of things as well. This is just one example. I think it's a good direction to keep going in. So some general thoughts on thoughts and advice on environments and tasks. Also, quick time check. I'm 1 minute over. Well, let me just.
It's okay. I mean, take time.
Okay, I can keep going. Okay, so some general thoughts and advice on environments and tasks. Understand what's already out there. Don't just like start building your own thing and without consideration of what's already out there. Highly suggest learning a simulation framework or 5 or 10 to be able to set up your own tasks and environments. You could start with the Colab that we shared today and tweak that, and you're off to the races. There's a lot of other good frameworks out there too. I think it's really useful you have a simulation, but like don't cheat. Don't try to cheat too much in terms of what the learning agent actually is going to have access to. So in the simulator, you could have the learning agent just have full state of every object in the world, but you can't get that in the real world. So if instead you force the learning agent in the simulator to only just use images, then that's going to transfer over better that sort of setup to the real world, of course. I think, again, it can be useful. We talked about it to have very visually clear and satisfying tasks. It can be useful to have the minimal complexity needed to sort of just test the desired skills. We talked about that with the Colab in terms of it's just a few blocks and a few bowls, but it sort of gets at the right level of diversity there. Might be necessary to have a bunch of diversity. And another thing too, maybe I sort of already tried to imbue this upon you, but like appreciate the work that goes into high quality sim environments because it's not easy. Okay, so data. There's basically just one thing I wanted to say here with data, which is that data in robotics is kind of tricky. Because data means collecting data in some environment under some policy. It's that last part which if you're not familiar with the way we collect data in robotics, that's the way, what? So I'll just talk through that real quick. So one thing on the environment is I just want to note that the environment in which you get your data can either be same or different to the environments that are used for evaluation. That's one thing to know. But with the policy, I think this is, again, quite interesting in particular to robotics. So in robotics, we care about temporally sequential data. So, trajectories of observations and actions, maybe other things too. But the key question always is, what was the policy that was used to get that temporally sequential trajectories of observations and actions? That's the key question. What was the policy's goal? So maybe you have task-specific data, but also another very interesting direction to look at is sort of just have task-agnostic data. That's it's helpful to be more specific than that, and sort of in different instances. But there's at least a sort of informal notion of quote unquote play data, where you just kind of have general data of an agent sort of interacting with an environment. Maybe it's humans that are just sort of playing around and just doing whatever comes to mind for them. And then also think about who is providing the data. So in addition to what's the goal, the sort of reward function, so to speak, of what the policy is operating under, who is providing the data. In the Colab that we provided today, the data that is used to train the policies is from a scripted policy. I think it's a really good recipe for just setting up, hey, you want to do a learning-based robot, train it to mimic some scripted policy. Super nice, because then you can just, you want to change your task, just change your scripted agent, you're done. You just need to generate the data out of that scripted policy. Another option is human demonstrations. Another very interesting option. I think it's the most interesting because I think it has the best sort of relevance to sort of real world robotics. And there's a lot of interesting challenges with multimodality and non-Markovian nature of human policies. Another option too, though, is to use somebody else's learned policy, or maybe you have maybe that's from RL, or maybe that's from something else. But these, I think, are kind of the three main options to help to keep these in mind. So again, you don't just have data that comes out of nowhere. In robotics, we have temporally sequential data. How is that data? Like, what are the actions that were chosen over time? It was operating under some policy. What was that policy? Very helpful to keep in mind. One that is, I think it's kind of niche, but I think it's like very important, and it's sort of unavoidable and sort of agnostic to whatever method you use, is just how you choose to parameterize your observations and actions. I'll go really quick because I am quite over time, but okay, maybe not go too quick. But so even agnostic to choosing the model itself, at the level of like what fundamentally are you learning? What are the observations and the actions into your learned agent? This is a hugely impactful practical choice. On the observation side, it's maybe the simpler side. Okay, whatever, images. We're at a computer vision conference. We love images. I do think images are the most important sensors for robots in most cases that I'm interested in. But there are a bunch of other things you get from the robot: joints, Cartesian, states, force torque measurements, maybe fancy tactile sensors. I say fancy because they're not really sort of mainstream. Yeah, they're very cool. Sound, I think, is underutilized. Maybe you have language coming in, a lot of different options. All this is very multimodal. It's very common in robot learning research to kind of pre-process some of the kind of raw imagey stuff into something that is then kind of considered an observation to your robot learner. So maybe neural fields or whatever it's going to be. A lot of different options there. But I think it's the action side where there's a little bit more subtlety. So a key bifurcation that Andy sort of hinted to in the Colab is that there's really two main ways that people parameterize actions for learning-based robots. One, and there's lots of pluses and minuses to both approach. One is kind of, Andy called it, we have a lot of different names. There's no like good standard names for these. So if anybody has a better option, let us know. But we sometimes call one like sparse control or motion primitives. But the key aspect is you move until you're done. So you sort of look at the world, you choose a thing, and then you might be moving without sort of revisiting your learned policy component for maybe a few seconds. And that is actually the type that's operating in the Colab that we gave out today. And some common parameterizations of how we might sort of parameterize the learner in terms of what it chooses, what is its action, is you can consider like sort of pixel as action, which is a really nice setup and works really nicely with a lot of computer vision tools. Maybe a pose, like maybe in a point cloud or in a voxel field is an action. That's one way to do it. I'll come back to why these are good choices to use this sort of motion primitive style. Another option it's kind of a misnomer, but the way that people usually talk about it is they call it continuous control. Note that by continuous, they're really referring to time, but it's not actually continuous time, but it's just kind of high rate discrete, sort of in the range of maybe 5 or 10 hertz, something like that. People usually call it continuous control. And there's an example on the bottom right of doing continuous control where at 10 times a second, the robot is deciding what it should do. And one of the advantages of this type of setup is that you can have actually like real-time reaction to what's happening in the world. A downside though is this direction is much harder to work in practice, I think, and to get to generalize over a lot of different scenarios, and it requires a lot more data. So you need to be like logging all of your data at full, maybe like 10 or 30 or higher hertz. It requires a lot of data. Whereas the motion primitives approach, you can formulate very simple, efficient learning. You need to log a little bit less data from the robot. I think in practice, also too, in terms of robots that are out in the world making money, most of them are using some sort of, if it's a learning-based robot, sort of all these like bin picking startups, they're all using this sort of first one of motion primitives. It's just a very practical choice. The second one, maybe in the long term, could end up, it's sort of, by definition, could kind of subsume the first one, but it's a little bit harder and trickier to get to work in practice. In addition to like what is, are you doing those 2 different versions I talked about? There's other ones, but those are the 2 main ones. Is how is it represented? The key thing here is discrete versus continuous. So let me just quickly say that classification and discrete choices are very nice, but in the real world, at least above the level of quantum mechanics, all actuators in the real world are continuous. So maybe you have a suction gripper, which is quote unquote a binary, on-off actuator. Really, underneath there's a bunch of physically continuous things with voltages that can be changed continuously. It's really continuous. But wait, it gets trickier than that because digital control is cheap to implement. And so actually, often, even when you have continuous things, it's PWM with a digital signal. And so I just kind of think about it as alternating continuous discrete turtles all the way down. It's really tricky, but I at least want to try to impress upon you that continuous is important, and you should at least consider thinking about continuous action spaces, which come with a bunch of trickiness to them. One quick thing on bringing it back to the real world. We just talked through a bunch of different concepts that can kind of be instantiated maybe out in sim, but again, I think it's really helpful to bring it back to the real world every once in a while. Just one example of this is that asynchronicity in the real world is really hard. So maybe in your simulator, you set it up with perfect discrete, Andy mentioned discrete MDPs, markov decision process, where your observations come in all at the same time, and you have an action all at the same time, and you can take as long as you want to. The time doesn't even really move linearly. You can take as long as you like to just decide what happens, and you're good to go. But in the real world, actually, all of your observations, they come in asynchronously, not necessarily at the same time. Sometimes the sensor doesn't hit its desired rate, and then also your actions are happening all asynchronously too. And also, by the way, while you are running your machine learning model, the real world hasn't stopped. Like, you have to deal with the latencies of the models, and there's all these tricky things that happen basically because of the setup. So that was the toolkit that I'm putting forward today. Is it fully comprehensive? No, but maybe you have, maybe it helped think about how different things fit together and what are some important things in the field. And again, I think there's a lot of nice connections with the Colab from today. The Colab is, I think, addressing definitely some of the big picture challenges in robotics by sort of tackling data challenges with, on the vision to action side, very efficient architectures, and then also leveraging large pre-trained models from other areas. So when Andy will go through later more with using LLMs in robotics contexts. We talked a little bit with Andy earlier about how the environment and task was sort of nice and simple and set up to test just what we wanted to do. The data was collected by scripted policies. The actions are parameterized as these sort of move until done motion primitives. And back to real robots, well, I can leave you to, if you end up forking the Colab and doing your own thing, you can go run something like this on a real robot, which I highly suggest you do. Cool. That's all I have. If anybody has any questions, I'm happy to take, but I'm also happy to go on to the next speaker because I did take more time.
Did you send the link? Okay, next up, we're going to have Michael be able to tell us about memoirs of a vision researcher.
Opportunity. Yeah. All right. Thanks for coming once more. So I'm going to essentially share my experience as a computer vision researcher in doing robot learning research. Some of this will actually be echoing what Pete just presented, which is good. So what's the objective? As mentioned, I would like to share my experience, my computer vision researcher point of view in doing robot learning research. I plan to talk about the difference between computer vision and robot learning in terms of the problem formulation, discuss about the opportunities, discuss about the main difficulties I faced so far, and also kind of share my experience by talking about a case study, which is about combining self-supervised learning and reinforcement learning, and as I mentioned, how it failed. Okay, so when I think about doing computer vision research, there are several components or several decisions I immediately think about. So imagine yourself as a graduate student and assume that you want to work on a research project, a brand new research project. There are several decisions you need to make. One decision is obviously what computer vision task you will be focusing on. It could be something like object classification, object detection, and so on, but you just need to make a decision. And then another component, once you decide on the task, is about the actual problem, research problem, such as learning better representations from large language models, which is a popular topic, and so on. After you decide on the idea or the problem, well, you'll need to design an approach. There could be various different types of model architectures. You can focus on the different losses. You can focus on the training framework. And yeah, there are so many. After deciding the approach, obviously, you also need to design your experiments. And we usually go with standard benchmarks like ImageNet or something like new and fancy like Ego4D. And if you actually ask me which part among these four is easiest as a computer vision researcher, I'll definitely say it's this one. I mean, once you decide to work on object classification, ImageNet is a must. We cannot really avoid it. We cannot convince anybody without testing it on ImageNet. So I don't even need to think about it. I just try to follow whatever people have been using in previous papers, and that's pretty much it. And sorry for embarrassingly bring my own paper as an example, but this is token learner. And if you look at the token learner, it actually kind of falls into this kind of flow. The task in this case was a general recognition, including like object recognition and video recognition, mostly image classification and video classification. And the motivation or the problem I wanted to focus on was essentially reducing the number of tokens in transformers and do some dynamic visual tokenization. And there was an approach to implement this in the form of the spatial attention mechanism. And then after that, the decision for me was pretty easy. I had to use like ImageNet, I had to use kinetics, I had to use like trace, and that's how things went. Now let us try to think about what we need to do when we are doing robot learning research. In terms of the task, there are many different robotics tasks, but in particular, what we are talking today is action policy learning. It's not really too different in some sense from what we do in computer vision. We are essentially trying to learn a function, learn a model that will provide you an action given your state, or give you some score, energy, of state given action. So in this case, your CNN, your transformer, or your model will be taking like two different types of inputs. But other than that, it's pretty identical to what you have been doing so far. There are different ways to train such model using like supervised learning, and it becomes more like behavioral cloning. Or you can use reinforcement learning, and there are like well-prepared theory, framework, code, and everything that's ready for you. So in some sense, this is what you need to do. And then the good thing is that there are so many computer vision researchers can benefit in terms of the research topic and the actual approach. There are lots of opportunities. We can actually contribute to robot learning research by coming up with better representations. Very surprisingly, many of actual like robot learning research papers, even like 1 year ago, they were still using like basic 7-layer CNNs, not even like VITs. I mean, if I publish a paper in computer vision saying that, oh, I use VIT, I'll get a huge amount of criticism saying that, oh, VIT is outdated. But in robot learning, even with the 7-layer CNNs, the reinforcement learning from pixels and imitation learning and everything was being done successfully. So they were taking advantage of it, but we all know that this is limited and there is a huge amount of opportunity. Also, as mentioned, the formulation of action policy learning naturally leads to multi-input fusion. There is like action input. Sometimes it's multimodal. There is other types of data, audio, language, sometimes the state vector telling the configuration of the robot, and there has to be naturally the fusion. And as computer vision researchers, we are really good model architects. So there is a lot of room for us to benefit. And again, sorry for bringing my own paper as an example. And this was regarding better representation and multi-input fusion. And in this case, all we did was run a very simple neural architecture search. So this was the kind of state-of-the-art model. As I mentioned, like 7 convolutional layers and so on. And we were able to find a better model by doing neural architecture search, and that was giving us better representation, allowing us to improve the task success accuracy. Another aspect is that once we have like robot images, many of these robot images are egocentric or robocentric. So first-person computer vision or egocentric computer vision research in our area can also particularly benefit robot action policy learning by doing better state representation. Another example will be about learning dynamics model. So if you are able to like learn to hallucinate what the robot will look like, essentially learning a simulator using GAN, autoencoder, or different types of approaches, you can directly plug something like this in as model into reinforcement learning as model-based reinforcement learning. So learning of generative model also has a good opportunity to benefit action policy learning. Another immediate thing is about sim to real. So there is a gap between simulator and real-world robots, but we ultimately want to benefit real-world robots. Meaning that we have lots of training data in sim, and we want to transfer that to real-world robots. And as computer vision researchers, we kind of, have this research area of domain transfer learning. And this is the exact application of domain transfer in some sense. And as you can see, yeah, this was done, and was published actually at CVPR. And you can see that there is, this is a hot topic. I mean, this is an important topic, and there is a lot of opportunities we see here. Okay, so these are lots of opportunities. I mean, and I'm just listing some examples, and of course, there are many, many more you can think of. But when it comes to experiment design, it's the opposite. When I was talking about computer vision, experiment design was the easiest. Somebody already did this for you, and you just had to follow. But here in robotics, this becomes a serious problem, essentially echoing what Pete also presented. Robot learning often requires online data and evaluation by its nature. What do you mean by this online data and evaluation? It essentially means that you need to run a robot in real or in sim for both training and eval. Okay, what's so bad about running a robot? Well, once we run the robot, there are things that happens. Your training set is essentially obtaining online data, meaning that what you use for your training changes every time you train. So based on different random seed, when you initiate the training, the data you will be obtaining on its way will always differ. And it's more like you are training your computer vision model every time with slightly different data set. And you are still expecting their accuracy to like be stable, the final result to be stable, which is not really. Another thing is that since you are doing online data, you are using online data, this means that your data changes during the training. So as your robot is interacting with the environment in sim or real, you get new data, and that's what you're supposed to use for your supervised learning or reinforcement learning. And because that it changes, there is a distribution shift, training this data distribution shift. And there is also data distribution mismatch because this online data will differ from training and evaluation. And here is an example. So this is the the graph I grabbed from the architecture search paper. The red curve is the new architecture, and the blue curve is the previous architecture. I mean, of course, the red is performing better, but what I want to look at is not that. I want you to look at these transparent bars. These are the standard deviation, and particularly look at the standard deviation of these, the blue curve. And I mean, they kind of actually overlap. So the difference between these two models is very, huge. So maybe based on this graph, we can conclude that this is better. However, when we talk about computer vision, we are usually competing in the realm of like 1% accuracy difference, like 2% accuracy difference. And if your standard deviation, if you can see here, is like 20%, and if your model relative accuracy is like 2% better, can you really tell that it's a better model, or is it just by your chance? And this is the difficulty you will be facing. Here is another example, and well, this is like an average, so at least the mean looks smooth over here, although something bad happened over here. However, if you just look at a single run, so this is an average mean over like multiple random seeds. But if you just compare like the same model over multiple single runs, this is how they look. So your evaluation changes almost at every training iteration. And even if you smoothen it, so this is nothing but a smoothened version of it, the same model actually ends up being somewhere totally different. And this is the situation you will need to face. So another aspect in it, so assume that you are somehow able to stabilize this. Assume that you are able to run this like 100 times, 200 times, thousands of times, and were able to establish some reliable evaluation metric. Even after that, there is an issue of standard benchmark. As Pete mentioned, every robot is physically slightly different. And every iteration, as I mentioned, every training iteration, every training random seed, your data will be different and everything will be different. And also replicating the exact same configuration is almost impossible. What I mean by configuration is that if the robot is interacting with objects, you need to exactly place it at the same configuration in order for you to compare your approach with someone else's approach on the other side of the planet. So coming up with the standard benchmark is an open problem. It's extremely challenging, particularly for real robots. And obviously, that leads us to take advantage of simulation. And there are several simulators covered in Pete's talk. There is also PyBlade environment Andy is using for the Colab session today. And these are some of the options, but the inherent problem of lacking standard benchmark in real robot tasks is a problem you will be facing. I mean, as computer vision researchers, we kind of take it granted that there is a standard benchmark. We can compare everything fairly, openly, publicly. That luxury will be gone. Okay, so the intermediate summary is that there are lots of opportunities for computer vision researchers, lots of topics we can benefit. And we also need to do something with the variance in training and evaluation. There are lots of distribution mismatches which causes such variance. So that's more like some of the things I wanted to share. And as mentioned, let me also go into one case study, which is about combining self-supervised learning, which is the concept from computer vision. I mean, visual self-supervised learning is the concept from computer vision, with reinforcement learning for robot action policy learning. So the main idea is to improve visual representation based on self-supervised learning so that we can do better robot learning. And this, as I have been kind of forecasting, is an example of where computer vision plus RL goes not as expected. So let's look at it. Intuition is, as mentioned, there is reinforcement learning for robot learning. And we are particularly interested in reinforcement learning from pixels. So your state is made of pixels or representations learned out of pixels. And then there is the self-supervised learning, which you'll be kind of more familiar with. It's a way to extract training signals from unlabeled data. And the intuition is to learn a better visual representation using self-supervised learning and ultimately achieve higher reward in reinforcement learning. So yeah, we benefit from self-supervised learning losses and then try to learn the better representation, which will eventually lead to the better reinforcement learning and better robot learning. And just to kind of give you what self-supervised algorithms, self-supervised losses we have been investigating, there is like MoCo, which is an example of like pairwise or contrastive learning. We have the same data, we have two different augmentations of the same data, I mean same image essentially. And we have two different types of encoder, which is the regular encoder and momentum encoder. And then we just say that, well, this is the same image, two different augmentations, so they should actually stay close within the representation space. And there are lots of variants doing something similar, like BYOL, SimSciam, and Dino. There are other types of self-supervision, such as like reconstruction based on autoencoders. There has been traditional autoencoders, there has been mass autoencoders showing that training your network, training your model together with a loss like this will ultimately allow the representation to be more generic. So yeah, there are lots of studies. And there are other types of self-supervised losses, like predicting certain things. Like if you rotate objects, you can actually set up your representation so that you will be able to predict how much it rotated. So there are things like that. And then there were previous work trying to compare or trying to combine self-supervised learning plus reinforcement learning. And this was a simple combination of soft actor critic plus autoencoder. And although it looks complicated, part of it is just soft actor critic training, like this part. And part of it, if you just look at the red arrow, is just the autoencoder training. So they were actually trying to put everything together and trying to jointly optimize different types of losses. And they show that it benefits. There was another thing, which is more based on the contrastive loss, essentially very similar to MoCo. As mentioned here, we have a robot image in Sim, and we try to get two different augmentations, which are essentially different croppings, give it to the encoder, and then try to minimize their distance, having this contrastive loss, in addition to having the action policy learning, reinforcement learning loss. And then there is another kind of story going on, sorry for confusing you, saying that, I mean, this was kind of interesting because it was the same architecture and people suddenly claim that, well, if we keep the architecture, the actual architecture, and then if we just get rid of the self-supervised loss part over here, it actually performs better. And there were other papers also saying that, yeah, maybe image augmentation might be sufficient for reinforcement learning, which were kind of contradicting what was claimed in this reinforcement learning plus self-supervised learning. So we wanted to kind of investigate what self-supervised learning losses will truly benefit reinforcement learning, and essentially what would be the recipe or what would be the framework to combine these things. How to make the self-supervised learning from computer vision literature best benefit reinforcement learning for robot learning. So we formulated a joint learning framework, what we call extending the previous CURL, or soft actor critic plus autoencoder. So as mentioned, yeah, this is very similar to CURL, But in addition to the reinforcement learning part, we attached many self-supervised learning heads. If we just have this one, this becomes very similar to CURL. If we add this one, there could be more self-supervised losses. And we try to optimize all these jointly within the same batch. We apply image augmentation, we apply reinforcement learning update, and we apply self-supervised learning update. And yeah, we replace this one with many different losses, and we try to compare them. How much time do I have? I mean, well, everything got shifted, but yeah.
You're good.
All right, I'll continue. So this was the general framework, and as you see, this can easily be converted into one of these, contrastive losses, or can be can incorporate computer vision self-supervised losses like rotation classification, shuffle classification, and even the reconstruction, which was actually used in soft-actor critic plus autoencoder. Yeah, and we can also take advantage of masked autoencoder instead by masking the input and then trying to reconstruct together with running the reinforcement learning objectives. And there are other types of reinforcement learning specific self-supervised losses, which are like reinforcement learning context prediction. So we can take advantage of the formulation to predict the current state, next state, action, and reward. And yeah, we can give some of these as an input, some of these as an output, and then trying to formulate the loss out of it without any annotation. So skipping the details, I'll just say that there are also like self-supervised losses specific to reinforcement learning context. Okay, that's enough for the setting. Now we wanted to evaluate which self-supervised losses are good, which are bad, by evaluating them in different environments. One is in sim, deep mind control suit. Another is more like a computer game, Atari. And finally, some easy real-world environment where the task is just simply to reach and stay close to the target object as much as possible. And here's the result on deep mind control suit. Red one is the vanilla baseline without any augmentation. All the other methods, whether they are using self-supervised loss or not, uses image augmentation. So blue are without any self-supervision. They are just image augmentation only. These, black methods, they are with self-supervised loss, and orange is with multiple self-supervised losses, actually just two. And we find some interesting observation. One, yeah, here's the basic baseline. And baseline was pretty bad, but some self-supervised losses were actually even worse than that. On the other hand, image augmentation, they were performing pretty well. I mean, compared to all these methods, even the worst kind of image augmentation was actually reasonably better than any of the self-supervision. So not all self-supervised loss have policy learning, and some of them actually even ruined the learning. It was not really good. I mean, so compared to the same thing using the same augmentation, which is this one, the use of self-supervised learning losses were only damaging the performance. Only like 1, 2, 3, 4 among these like 10-ish self-supervised losses were actually better than just the augmentation. And also, if we carefully hand-tune image augmentation parameters, we find that they actually perform better than any of single self-supervised losses. They actually perform better than combination of multiple self-supervised losses. So this is actually showing that existing computer vision-based self-supervised losses actually fail to outperform carefully designed image augmentation, meaning that they are not really compatible. So we also try to investigate how we can actually combine multiple different types of self-supervised losses by doing evolutionary search. We try to combine multiple different types of losses using an evolutionary algorithm. And based on that, we were able to find some optimal amount of like parameters combining these different types of losses and come up with something like this. And the observation here is that this combination of everything actually is better than everything, which is good, and it's still worse than image augmentation only. So use of self-supervision, regardless how many losses we used, was still inferior to carefully designed image augmentation. Meaning that, okay, what's the point in doing this? So we also try to confirm whether this holds in real robot environment by running a very simple, robot test. It's a richer version, real world version of the richer in simulation. And the goal is to just, get closer to the orange cube as possible. And here is some interesting results. Without augmentation, given a limited amount of data, we were not able to learn anything. As soon as we give augmentation, it learned actually well. And it actually learned better than use of the self-supervised learning loss. CURL is one of the kind of most typical self-supervision plus reinforcement learning. And we were able to see that the image augmentation itself, the basic vanilla image augmentation, was sufficient to outperform CURL. The DRQ, which was really good in DMC, didn't really work very well here, meaning that they were kind of overly optimized, like, to DeepMind control suit parameters. Maybe the hyperparameters were off. This is image augmentation only, and this is image augmentation only, relying on different, augmentations. But in the end, we see that the augmentation identical to CURL, what was being used in CURL, is actually better without self-supervised loss in CURL. So that's pretty much it. The conclusion we were able to observe was that the role of self-supervised learning, at least within this joint learning framework, trying to jointly optimize everything, is usually very limited. While the selection of image augmentation is sometimes much more important. We were able to kind of find that there is no golden self-supervised learning or image augmentation for reinforcement learning that generalize across environments, which is a bit disappointing because we kind of try to combine self-supervised learning from computer vision, reinforcement learning for robot learning, and yeah, it didn't work. Better framework probably is necessary in combining them, not just this joint optimization framework. And whether we need a better loss function or not, that's an open question, I think, from here. So that pretty much kind of concludes what I want to say today. And just let me know if you have any questions. Yeah. If you can use a microphone, that will be better.
Thanks for your presentation. Actually, I'm also recently hired as
Uh-huh.
This meeting is being recorded.
Oh, this mic.
So okay, this is a good question. This is a good question. We follow joint optimization framework instead of pre-training the entire model with self-supervision and then fine-tune model with self-supervision. In the archive version of the paper, we also have the pre-training framework tested, evaluated. It gave us a similar conclusion, and I didn't include it, but it gave us a similar conclusion. And the reason why we use joint optimization framework is because that was the most popular, or so there was CURL, which was very popular, and there was like soft critical plus autoencoder, which was also very popular. And they all use this joint optimization framework, and we try to extend whatever has been the mainstream in robot learning in terms of self-supervision plus reinforcement learning. So that's the reason why we used, and I think the reason why they initiated, formulated this framework is because, as mentioned, the training data is kind of changing during the online interaction with the environment. So it was pretty natural that the batch is updated at every training iteration, And they wanted to apply the self-supervised learning laws and the reinforcement learning laws for every batch they are obtaining. So I think that's how they came up with it, and we just try to follow it.
Yeah. Actually, I also had a drawn a similar conclusion for the SSL doesn't help. And here's it's a general question. So do you think like SSL is a kind of beneficial, so do we have to collect lateral data?
So the question is whether self-supervised learning is really useless for robot learning. My answer is no. I think there is a hope. So if we are only taking advantage of online data, and if we are using the current this joint learning framework, the answer is yeah, this is not doing anything. However, when we switch to pre-training framework, there is a potential that we can minimize the environment interaction by taking advantage of already collected data. I mean, we can even take advantage of the data on YouTube or whatever data that's out there. And in that aspect, pre-training framework has more potential in utilizing such data with self-supervised losses. So there is more potential in that direction, definitely. And I think we are simply lacking, we have not yet found the good framework to combine self-supervision and reinforcement learning, which is up to all of our future study. All right, thank you.
Okay, so it looks like this is a problem. Maybe just switch to it. Okay. Oh no, the mapping is so weird. Maybe I should figure it out. Maybe go for
You can mirror the screen.
yeah. The problem is the dock is up there.
I mean, you can mirror it.
Okay, do you know how to do it? Like I don't know.
Just put settings. Fine, it's okay. Yeah, mirror.
Okay. All right. Let's check. Yes. Okay, cool. Sorry about that. Oh. Yeah.
We can't see that over here.
Okay, I guess I can just I'll just work with it. It's cool. Okay. So today.
Let me try over. So let's
Nice.
make it smaller.
Thanks. Okay, so my name is Samir. I'm here as part of the Columbia Artificial Intelligence and Robotics Lab, and today I'm going to be talking about using existing zero-shot models to do robotics tasks. And I have this kind of provocative question here, which is no training, and I specifically mean no training for robots. And this seems kind of like a ridiculous question in light of all of the talks and wonderful like tutorial that's happened so far. So let's start with a bit of motivation. So if we look at the backdrop of what's kind of happening in NLP and in vision, there are these large pre-trained models that are really sort of making a splash, and they're doing all sorts of cool things. And most notably, they're doing them zero shot in a lot of cases, or at least this is a very new kind of line of study. So here what happens is we're going to train on a specific pre-training task, but at test time, we're going to test on unseen tasks. But something about the structure of our pre-training actually allows us to do these tasks downstream. So this is incredibly exciting, and it then allows us to pose this question of, can we actually use these models more or less out of the box, maybe with algorithms around these models in order to start to do some robotics tasks. Okay, so to start, just as an overview of this talk, I decided to ask GPT what this talk would be about. So I prompted it with the CVPR tutorial on using large pre-trained models for robotics. And this is what it gives me. I'm not going to read it, but it does roughly outline the talk, which is interesting. So first, I'm going to talk a little bit about pre-training at a very high level and sharing some success stories from both NLP and in vision. What I'm not going to talk about is how to use sort of robotics data in order to pre-train. This is a super exciting direction and something that I do think that we should all be thinking about, but it's sort of not within scope for this talk. So next, I'm going to talk about a few applications of these sort of existing large pre-trained models, specifically for manipulation, planning, and navigation tasks. And then GPT also wants me to talk about object detection, but I'm not going to do that. And then finally, I'll talk about a few limitations and some exciting future directions, hopefully inspiring many of you to start working along this direction. Okay, so just a brief review of pre-training. We have this function f, which is randomly initialized. We choose some task, and we want this task to be sort of general, but also pretty diverse. So the rainbow here highlights the diversity, and then we get this checkpoint, which is f0, which is our pre-trained model. So now what we can do is, this is sort of the standard fine-tuning setup, is given data for our downstream tasks, say D1 through Dn, we can fit a small number of parameters, either like a linear layer of some sort on top of this representation, or we can do end-to-end fine-tuning. So the thing that I think is really interesting is now with these large models, you can start to not necessarily see data for these downstream tasks and still get sort of respectable performance. It's important to note that the gap for some tasks in NLP and vision is considerably high compared to the fine-tuned solutions, but in a lot of cases, this works surprisingly well. And we'll talk a little bit about how this is working in a second. But one thing to note is that it's not just about the objective that you choose at pre-training that allows this to happen. There are a few other magical components. The first is data. So your data probably should look more like this. And then you all probably see where I'm going, but your models should also probably look more like this. So they don't really fit on the slides anymore. So this is something that I want everyone to kind of keep in mind, just because I'm going to be talking about the objectives and the algorithms, and this is kind of the intellectually interesting part to talk about, but a lot of the success is really being driven by this kind of story, and it seems to be working so well that we really can't ignore it, in my opinion. Okay, so I'm gonna breeze over this, but here are like a few success stories in zero shot doing okay. So question answering in NLP seems to be We seem to be on the right track there. And then image classification in the vision world. So what seems to be getting us here, at least on the objective side, so I'm going to talk about two kind of high-level objectives. The first is language modeling, and the second is this vision language contrastive objective used in CLIP. So with language modeling, the task is going to be pretty straightforward. It's just kind of predict the next word in the sentence. So by training a model to do this on sort of very large corpuses of data, it starts to like learn some interesting things about language and the way that humans might pose questions and do other things. So the cool thing here is that we can now do things zero shot at inference time. So here I've posed a subtraction problem to GPT, where I tell it I have 7 apples and I eat 3 of them, and I ask how many I have left, and it tells me that I have 4 apples. You can also imagine doing kind of a sentiment analysis type task. So here I have the phrase, I love computer vision, which we all do. And GPT agrees, it's a positive phrase. So the point here is that we haven't explicitly trained this model to do sentiment analysis, but it kind of comes out of the wash in this kind of language modeling objective. So similarly, we have some kind of fun objectives in vision. So there's this clip objective wherein we're going to try to align representations of images and corresponding captions in a feature space. So here we have this dog and then the caption, this doggy is adorable. And we want the features for these things to be very close in some embedding space and far away from sort of this dissimilar concept of LOL, that's a weird frog. And the cool thing here is now we can define arbitrary classifiers at test time. So given a caption, a photo of a dog and a photo of a frog, I now have, and the corresponding text features for these, I can now ask the question, is the dog feature close to the image dog feature? And if that is the case, then I'll classify this image as a dog. So this is kind of how zero shot emerges in this case. Okay, so we have some zero shot capabilities. So we have lights, in parentheses language, camera, which is the vision. What are we missing for robotics? And GPT tells us action, and more specifically motor control, which I think is probably not too far off. Okay, so the first thing that we might think to do is we might want to pre-train the robot like we did in NLP and vision. So the robot wants pre-training too. And this is maybe possible, but I think it's probably hard for a lot of the reasons that sort of the earlier presenters mentioned. And I think one major thing is data here. But people have definitely been up to very cool things on the data space and also the algorithm space. So that's sort of, maybe the answer is maybe, but maybe we're just not there yet. Okay, but let's ask GPT, can I pre-train the way that you were pre-trained? Any guesses on what GPT is gonna say? Okay, GPT says no, you cannot, pretty like definitively. So the robot's pretty sad here. So what do we do now? Do we sort of give up? No, before we give up, maybe we can just ask for some help. So we say, okay, no, you cannot, but can you sort of help me? And GPT says, yes, I can help you, but still you can't pre-train like I was pre-trained. So it's pretty adamant that you can. So here's the kind of working idea now is that the robot is sort of going to take what it's going to get, and how are we going to adapt GPT and CLIP in order to do robotics and models of the future, presumably. So what do I mean by adapting? I could mean like a couple of different things. So one thing is fine tuning on top of these representations. Another could be zero shot inference, so directly using their zero shot capabilities for robotics. And I'm going to talk about a subset of this work. So Clipboard has already gotten like a lot of mentions, so I'm just going to kind of breeze over that and then focus on these two works on using sort of zero shot methods. Okay, so I'm actually just maybe going to, since we've talked about Clipboard quite a bit, I'm just maybe going to show their demo videos, which I think are really cool. So here's like an example of, you know, closing a loop on a piece of string and then like picking up cherries. Okay, so so as sort of Andy and others alluded to, you kind of have to do this training on top of CLIP. And so I think it's important to think about what we're maybe losing by doing this. And here are some possibilities. For one, you could imagine losing a bit of robustness. So these CLIP models are incredibly robust to a lot of distribution shifts. But when we start training them on sort of these target demonstrations in more of these tabletop settings, maybe we start to like sort of throw away those really nice properties. Clipboard does show some kind of like generalization of different concepts, but maybe it's not as general as sort of the original clip model. So another alternative, I guess, is to kind of use these models zero shot. So the first paper I'm going to talk about along this direction is this Huang et al. Paper called that essentially uses language models as planners. And the high level idea very much is the title of the paper, which is that by sort of prompting these language models, we can actually get them to give us high level plans. And so what do I mean by a high level plan? You know, maybe getting to New Orleans, you would make sort of a high level plan in order to get to New Orleans, you would buy tickets, you'd jump on a plane, et cetera, et cetera. And so it's kind of exploring that direction. So as input, we're going to give a very high level task, such as browse the internet. And then as an output, we want sort of a sequence of actions that will achieve this task. And in this paper, the actions are pretty abstract, but you can imagine for each abstract action, you could maybe have a bunch of like lower level actions that implement that high level action. So this is kind of how these things are related to robotics ultimately. Okay, so the first thing we're going to do is we're going to have a frozen large language model, and we're going to feed it in this browse the internet, and then prompt it with step one, sort of trying to get it to come up with what the step is. So maybe it'll say something like walk into the home office, but walk into the home office isn't something that our robot necessarily knows how to do. So we have to kind of do this arbitrage step of retrieving from the actions that we do know how to do, like which one is the closest. And we're actually going to do that with another language model called BERT. But the thing to note here is that we just have a feature for walk into the home office and features for everything here. And we're just going to kind of do like a matching step. And then we're going to just append this to the prompt. And now we have moved to the computer room. And then we can imagine just doing this kind of over and over again until we have some kind of stopping condition. This is how we're going to get our actions. And so this is kind of a demo from their paper of this agent executing these high-level actions. And then it kind of goes to the computer and it's looking at Google. Okay, but ideally we want vision also. So the last paper I'm going to discuss is some work from myself and collaborators on trying to extract more like actionable information specifically from vision language models. So this is the clip on wheels work, or CAL as we like to call it. So the high level idea here is that zero shot models can classify images zero shot, as I kind of described earlier. So maybe we can use some vision tools such as like saliency methods or relevance maps to try and extract localization information from these models. And then we kind of get a very simple heuristic, which is when we've localized the model, plan to it in some kind of a map, or if not, just explore until you do generate a view where you've seen the object. So it's a fairly simple heuristic or a fairly simple algorithm. But the cool thing is that we don't really have to do any training to do this. And also we can deploy zero shot in these two environments, Habitat and Roberthor, which have very visually distinct appearance. and then start to gain a little bit of understanding about like the robustness of this method to some distribution shifts. So here we have as input like RGBD image and then language prompt of the targets, in this case a plant, and we're going to output some discrete action, either a movement action or stop, saying that we've found the object. So again, we're going to encode the image and the language to get the features. And then we're going to use like a modified version of a gradient-based relevance map method. So I think one that is very commonly known in the vision community is GradCam. So this is kind of a modification for that for VITs with a few other things going on. And then using geometry, so something way throwback potentially in the vision toolbook, we're going to, or toolkit, we're going to kind of create these relevance maps that are kind of these top-down things that we can do using like pose estimation plus back projection. And so now we can ask the question, should we explore or should we exploit? And if we are confident that we've found this object, in this case the plant, then we just like kind of plan to it using a planner. And if not, we just like explore some more. So yeah, so I mean, arguably this is like a little bit of a hack, but the cool thing is that you don't really have to train. So yeah. And I have just a short little sequence here where we're looking for the plant. We're gonna like maybe explore around. Oh, we found it. And now we go into planning mode and we just move there. So yeah, that's that. So I think I'm a little bit close on time, but I just wanted to say that these are kind of the limitations of kind of using these large models. So there are known biases in these models, like for example, racial biases. And I think we should really be taking them seriously, especially as roboticists and vision folk, and making sure that these biases do not like affect our downstream robotics algorithms. So I think that's a huge limitation that deserves like a lot of study. Also, there's still like a pretty huge gap between a zero-shot method and a fine-tuned method. So kind of closing that gap, I think in classification, that gap is shrinking rapidly, but in some other tasks, that's sort of definitely a limitation. And then paywalls, I'll mention is another one. Like a lot of these models are behind paywalls. And maybe in the future, this will become more common. So it's just something to keep in mind. And on the direction side, basically these models are very powerful, and I think they kind of open up some new like algorithmic possibilities, and we should start thinking about those instead of necessarily just trying to learn everything. Although I think learning probably plays a part. So yeah. Oh yeah, if people have questions, I can take.
Yeah, I have a question. Thank you for our great presentation. So I wonder if you guys just mentioned that you also considering about retrieving the robot action space, right? So yeah, I'm just curious about, so because we keep training on the feature language because we want to extract the information from high dimension to the low. But robot action the low space and in many cases, we already know the dynamic model of robots. Do you really think we need to train on the robot actions?
Yeah, so that's a good question. I think part of the reason that that this direction makes sense of leveraging the large pre-trained models is because we actually do know how to plan. So if you know the sort of robot geometry, then you can maybe implement a lot of low-level actions like through planning frameworks. Like I said, I don't know if this is like necessarily the answer long-term, but it does allow us to like do things with these kind of large models as kind of doing the reasoning behind the planning. Yeah. Does that answer your question? Yeah, so maybe you wouldn't necessarily want to have a large model to model actions, although that could be interesting as well. Yeah.
Makes sense. question on this data.
Sure.
Have you thought about incorporating this series of language model into the exploration strategy that you use in heuristic based exploration right now? But these models have sense of semantics, common sense that will help you navigate those.
Yeah, definitely. I think that's a super cool thing that I've been thinking about that a little bit. Yeah, so I think in the traditional navigation literature, people feel that priors are pretty important. So like, for example, if you're trying to find, I don't know, a fork, then knowing that a dining room is close to a kitchen is probably close to a fork is sort of helpful for efficiently navigating. Yeah, so maybe I think it's very likely that language models encode a lot of these priors and that maybe they can be used. And maybe kind of like the Socratic models kind of line of work, I think kind of gets at this too. Yeah. I mean, I think it's kind of sort of maybe way of extending clip-on wheels to do this is instead of having the high-level target be the plant, maybe trying to prompt GPT in a way to get a sequence of actions, and then, I mean, just off the cuff, maybe trying to get GradCam to figure out, or trying to get Clip to figure out or goal check along the way, like what have you actually done? Like where in the sequence are you? And then it's probably more like a tree-based thing than a list-based thing, but I don't know. Yeah, so yeah. Okay, cool. Thank you. Okay, can folks hear me? Okay, sorry about that.
I don't see you.
Yes, now. It says yes now.
Okay, great. Cool. So with some of these interesting language model capabilities, this last part of the demo ties everything together into this final system that allows prompting GPT-3 to come up with, given a list of objects, for example, as detected by the visual language model, take in the human command and then generate step-by-step pick and place commands that it would feed into clipboard. You might notice that at least the structure of the prompt here that we feed into the language model is of code, or at least looks like pseudocode. And there's a reason for this. We've been playing around with language models and how we can get them to be very structured in their plans. And sometimes models like GPT-3 might accidentally go out of distribution of the way that you intended to. So pseudocode is actually a fairly good way to keep that constrained into, because generally code is quite structured, and the way in which you change your prompts to sort of fit in code is like coercing the model to zoom into that part of the data distribution that's looking at code. What this prompt here is several examples of what kind of outputs we expect GPT system to respond to. So for example, if you just directly copy paste this into Playground, you can play around with what potential outputs it might be able to generate a condition on some task. So say, for example, we can take a list of objects, copy paste that in, say that we have a blue block and a blue bowl and a red bowl. Here we formulated user input from a human as comments inside the pseudocode. So say sort all the blocks. Okay, so I prematurely, or I stopped it here because it was going on to generate a new list of objects. But really the plans that are being generated by the system here, robot pick and place, red block into red bowl, blue block into blue bowl, is an example of how we're using GPT-3 to generate these plans conditioned on the things that it sees from a visual language model. It's actually fairly cool, the kinds of things that this expands into. So for example, if you list out what objects could be, instead of just a red block and a blue block, if you say that you had a banana and maybe a bag of chips, add in Coke, add in water. And we can change this input prompt here to be something like sort the healthy snacks from the unhealthy ones. And we'll add a stop sequence here just so that it stops when it's about to generate a new sequence. Then it'll respectively give you a list of pick and place actions that we put the banana in the blue bowl, water in the blue bowl, and then Coke into red bowl, and bag of chips into red bowl. And this is interesting because it's processing the code in the structure that you expect, but it's also leveraging a little bit of out-of-domain information to kind of figure out what's healthy and what's not. So the extent to which these planners are capable of these things is fairly unbounded, and I'd encourage most folks here to explore what these things can do. It's quite exciting. Cool. And just to, one more comment is that all of this is just information that's stored inside the language model from internet scale data. So I'm sure that there's ways in which robots can leverage more of this. Cool. So in the Colab, once you've run all, you'll the end part, and some of you might have been training your own models too. The Colab at least sets a max train step to be 40,000, but you can increase this to a higher number just for more robust performance from the clipboard model. But the tasks that you can do now is, let's just reset the environment real quick. So here we're just going to add the set of objects that we have and run vials so that it can generate a scene description of what objects are available. And what the code does is fairly simple. It takes in the outputs from vial and appends that as the scene description. And then you feed that as context into the language model. And whatever is here in the user input is essentially the comments in the pseudocode. So here we'll just go ahead and run this. Sort the blocks in the way you think it best fits. the LM will say, pick the green block and place it on the green bowl. Specifically, it was generating it in the form of pseudocode, but because clipboard takes in an actual sentence that's of the form, pick the blank and place it on the blank. This is literally just using Python execution to run this function pick and place so that it generates the string that it feeds into clipboard. Our previous demos actually just directly would feed in the language step generated by the language model, but ever since we switched to this code-based version of generating plans, it started getting much more robust results. Yeah, so you'll see that the plan that's being generated, pick the green block and place it in the green bowl, and it looks like it's doing that for the first step. It'll generate the next step, pick the yellow book, place it in the yellow bowl, and then finally placing the blue block into the blue bowl. I think we can do all sorts of interesting things too. For example, if we say, we can reset this environment real quick. This is untested, but maybe we can say something like mix the blocks, or put the blocks into mismatched bowls. Pick the green block, place it in the yellow bowl. Cool. And the next step, pick the blue block and place it in the green bowl.
Also, you can see a lot of the time it's just rendering the images from the videos.
Yeah. Yeah, Pete was saying that the vast majority of the time in which it's taking is just having it roll out in the physical environment or in the simulated environment and then recording the video. So actually, this is an interesting point because if you're doing research in real world, oftentimes you're also gated by just having the time spent on having your robot run the thing. Looks like it didn't generate a third step, so I'm not sure what happened there. Yeah, so this is a kind of a great segue to go into limitations. So if folks are interested in taking this Colab and pushing it further to see what are interesting research problems you'd like to tackle, here's a big list. So the first one is in this Colab, we're using a very naive scene representation. We're just running object recognition, we're providing a list of that into the scene. But you could imagine that there's value in trying to figure out how do we better describe this scene. Are there prepositions, ways in which you can describe the spatial relationships of the objects? You have a bowl inside of a cabinet located next to a kitchen counter. All of that information could be useful for planning, but isn't actually being provided in this system here. So it'd be interesting to see how you can go into higher resolution kind of scene descriptions and assign more fine-grained attributes even to the objects themselves in addition to kind of the relationships between each other. Yeah, and as I mentioned, there's no spatial relationships. Say that you had an object on top of another. Currently, the system won't know how to say, pick the thing that's on top of the red block. So how do you specify that to the language model planner would be interesting. There's object bounding boxes are definitely not enough, especially if you're interacting with various different real world objects. You have t-shirts that are lying on top of beds with blankets everywhere. How do you get a system to describe all of the nuances of how a deformable object can be rearranged? So another example here is, say the task was grab a tissue from the pants pocket. You might need to look into visual language models that are able to give you saliency or relevance detectors of where the pants are, or where the pockets are in the pants and where is the tissue. There's also this question of how this links into low-level action. So say that your robot needed to move to a different view to get a better sense of the scene around them. So how do you get the system to, for example, do some of the language-based exploration stuff that maybe Samir had mentioned as well. Bounded perception outputs. So the visual language models here, we are using Wild and we're using Clip. And specifically with Clip, it's using image plus object labels, which is a predetermined list, and feeding them as input to get a similarity score. So that's okay, but what we really want is a visual language model that can give you, sort of generate descriptions. Just by looking at an image, understand what are all the things that are in the image, and then naturally generating it. Because then that would mean that you don't have to provide a list to the system beforehand. So at least in this Colab here, we've restricted it to say, okay, here are the full set of objects in which you could potentially grasp, and here are all the potential colors you might see it in. This is still a limitation because what if your robot was put in a new environment? How do you get it to generalize the diversity that you might experience in the real world? Another follow-up on that is there's no visual closed loop feedback that's happening here. So you might notice that the plans are being generated, but there isn't, for example, a visual language model that's interweaved into the planner and constantly giving it feedback. Did you do the task successfully? So this is interesting because if the policy, for example, fails one of its pick and place actions, then it's just going to continue doing the next step. It's not going to be able to say, let's redo that previous step. Figuring out how to kind of interweave the back and forth between the visual language model and the planner are all very interesting problems to tackle. So at least in context here, there's no, in the Colab, there's no replanning due to downstream policy failures. Yeah, and also no recovery modes from perception failures or occlusions. So say that Wild in the beginning did not detect the set of all objects that were in the scene. So say that, for example, in the scene here, it only detected the blue bowl and the green bowl, but it didn't detect the yellow bowl. So now the language model only knows that there exist these 5 objects, and if you task it to sort all of the blocks, it might not generate a plan that is correct. And the last point here is we have bounded planning outputs when and how to learn new low-level skills. In the demo that we showed where it's taking in human feedback, it can only construct a plan based on the power set of all of the skills that it knows how to do. And this is the space of the skills in which we've trained Clipboard to be able to execute. Back up here, if your Clipboard, we've only trained it to be able to pick some particular color block, place it into a bowl, or also place it to the top, bottom, left, right side, or the top, bottom, left, right corner, or middle. If you ask it to do a task that requires chaining pick and place actions that are beyond these sets of actions, then the system won't be able to figure that out either. So for example, if you ask it to construct a smiley face with all of the blocks, it may not be able to do that well. I think it'll fail miserably. So I think finding ways in which we can get these low-level skills to be more expressive, or at least including more low-level skills in general, and having a planner maybe also be able to say, okay, if these low-level, if this high-level request generated me a list of steps, and one of these steps is not inside the list of things that I know how to do, then I need to maybe train a new policy that can allow me to do that low-level skill on the fly. So there's really a question there, which is how can we have the known primitives that we have trained to expand and be dynamic over time? So I think these are all just kind of different directions in which you can take this Colab, and each one is sort of a very ripe research area. I think that it's all green fields, basically. A lot of these things that, you know, if you tackle on the next couple months, it's definitely going to be new stuff. So yeah, definitely worth thinking about. Cool, any questions? There's one from Zoom. Do you have a few examples of interesting language instructions just to see what kind of instructions you test?
I think that was before you did some examples.
Oh, okay, all right. Okay.
The second one's a good question.
The second question says, I get a few cases in which GPT-3 generates an infeasible instruction, e.g. grasp a cyan block, but there's no such block. Is that expected, or did I run something incorrectly? One thing to double check is to ensure that you fed in the object description right before you asked it to generate the plans, so that it knows what objects are available in the scene. It's possible that, for example, if you prompted it to do a new task, then it might be relying on the object list that is far inside of its context, and that would be no helpful at all. So updating that list of that scene description is one way to fix that error. Are there any other questions? Yeah.
And probably build upon my previous question, but so have you thought about using language models for exploration and search-based tasks, and how would you use them for planning or organizing search tasks that have these that require the agent to explore, and it will need some feedback at certain times that to replan the step, like whatever it has.
Yeah, the question was related to using language models for exploration. I think I think that's definitely a very exciting area, and in particular because these language models have seen so much. They've read novels, and some of these novels have captured what indoor environments typically would have. You would have a kitchen, you would have an oven, various objects inside of it. So leveraging that context as a way to potentially build, for example, a graph of sorts that's sort of treating it as a knowledge base of what potentially could be inside of an environment feels very promising. And then maybe having your robot sort of digest individual steps that iterate through that kind of representation might be very cool. That's just like a very specific thought, but I think in general, anything that you do in this space could be very exciting.
And how would you, what would be the way, or like just in general, how would you take feedback? So given you use some language input to plan some action for exploration, but you would still need feedback from the current state of the agent to replan the next steps.
Mm-hmm. Yeah, I think that's a great question and ties into potentially representations of uncertainty. So when you're exploring and there's parts of the space in which you're more curious about than others, maybe there's a representation that is outside of the language model space, but you have information of storing what the robot is most curious about. And then maybe finding a way in which the more that you traverse the most uncertain areas, the lower the uncertainty score, etc. So I think that is, yeah, very interesting indeed. Yeah.
There's another question from online, Andy.
How would this system perform in an M with very specific non-general objects? I see. So specifically in industrial automation tasks, for example, if the object has a very particular geometry, I think one way in which you can make it work on those specific objects is to still have some way to ID them or reference them. So for example, say that in the language model planner, we replaced the strings with IDs, for example, obj 345 and obj 321. And then maybe replicate that list, replicate this string inside the list multiple times in order to show how much frequency you have, and then just have it be able to, let's say that we have 3 of obj 321. Then sort the objects. Okay, not by the length of their name. Period. It's adding in comments. Okay, so that did work out well. I think maybe being creative about how you reference the objects. One thing that's interesting about language models is that you can try to formulate a unclear problem in one domain into a clear problem in another domain. So what I mean is that if you, for example, gave one of your objects an alias red block, and then you just had a dictionary that was sort of mapping that to the cat name or cat file, then you could potentially still have the system be able to benefit from the high-level reasoning of putting in general objects into each other, but still being able to reference specific objects.
Also describe a lot of the object in language.
That's true. So Pete says you can also describe the object in language. So if you have particular,
let's say you have a Stanford bunny, you could like describe everything it needs to know about the Stanford bunny. You know?
Yes, yeah, you could, if there are objects that you want to work with and the attributes are relevant for how the robot should manipulate it, you can add in a bunch of different descriptions to it. The example that Pete was mentioning is the Stanford bunny. You can have a description of everything that you know about the Stanford bunny being appended to information about that object. Oh, you know what? I think the temperature term was responsible for these things. So what happens if we fix that? Okay, just kidding. That did not fix it. Okay, so these things still require a little bit of prompt engineering, and it's worth playing around with. Okay. Cool. Any other questions from the crowd? Yeah.
Yeah, thanks for the quick question. So yeah, these language models are really hard, and you know, we saw some really cool examples, but some examples don't work so well. Do you think the way forward to solve this is just we train on bigger and bigger scale, or there's like a fundamental change in like training objective architecture that is getting things to work 100%?
Yeah, I think in order to at least tackle some of the specific problems that we've shown today, one very easy fix is just through adding the examples, few-shot prompting. So adding in several examples of the task in the mode that you expect it to be in inside of the text prompt. So one potential failure case for why this happened is because up above, we've been using yellow blocks and bowls all the time as examples for few-shot context. But say that you started copy pasting some of these examples into the prompt as well, then you might be able to get the system to get better performance. So that's one way to immediately use the existing models that we have. I do think that maybe at least we've seen a couple newer language models, including Palm from Google, that shows that as you scale these models, they also tend to become more performant in a lot of the tasks that maybe some folks consider previously out of reach, so logical reasoning questions, etc. And I think that so far we've been seeing a lot of mileage come of that, and I think that it's possible that sort of just by using the latest and greatest, we'll get better performance. Cool. Any other questions? Okay. I guess that's the end of the tutorial. Yeah. Well, thanks everybody for coming out. Thanks for sticking till the end. So for folks that don't know, we've left links to the Colab on the official website, and yeah, feel free to reference it there. Thanks.
We put the slides up?
Oh, yes, we'll put the slides up.
We'll put the slides up. Okay.
Yep.